Okay. Last class we were talking about the evolution of phase diagrams based on thermodynamic principles. We took up two parameters which are basically the omega s and the omega L, which is nothing but the interaction parameter in the liquid between A and B and interaction parameter in the solid between A and B, and used them to basically see how a phase diagrams evolve from an isomorphous system, and you get an isomorphous system when both of them are close to 0, and as you start varying one keeping the other one fixed, how does the phase diagrams evolve. So we tried to see that, and today I just had brought you an image from one of the reference, as you can see here. This is from Masalsky, published in Metrans in 1999, which gives you a flare of how really the phase diagrams evolve. Yesterday I was talking about that. You can see here on the left axis you have the omega s, and on the top, which is the x axis, is the omega L, and you see how as you start varying these things, how various phase diagrams come, and you see when you take both of them as 0 0, okay, that is what ends up you the isomorphous system. And if you keep omega L as 0 and keep decrease or keep the omega s as 0, keep decreasing the omega L, make omega L more and more negative, you see when it is minus 10 and when it is minus 20, what you see, you start seeing the pseudo eutectic phase diagram evolves. So the liquid becomes more and more stable, so the liquidus curve starts plunging down, and as you start seeing, you see more and more of liquid stability there. And on the other side, keeping the same the omega s as 0, and let us say increase the omega L to positive side, again you see that you start seeing that, because the moment omega L is positive and omega s is 0, that means solid is more stable than the liquid, and as a result solid stability regime increases and you start seeing a congruent melting case develops. And similar thing can also happen when omega L is omega s is negative. Okay. For example, keeping omega L as constant at 0, and if you make the omega s negative, this is what you see in the diagram below, where you see the moment you have minus 15 for the omega s, you again start seeing the, for the same omega L being kept as 0, so you see the congruent melting starts evolving. So you can see that we can have either this under the ideal conditions, you can have a pseudo eutectic type when the liquid is more stable, when the solid is more stable you start getting what is called the congruent melting, which is an indication of the formation of intermetallics. And if this becomes stronger, that means if the omega s becomes more and more negative, you would actually see that intermetallics start actually evolving inside the phase diagram. And this is as far as the either omega L being negative or omega s being negative. But if you think if omega s is positive, what is going to happen, keeping the omega L as 0, and if you start making this positive, for example, you see this is plus 15 and everything is kilojoules per mole, all the numbers that we are talking are basically the enthalpy units, because omega s is nothing but the enthalpy units, because it is an interaction parameter, and that multiplied by xa and xb will give you the actually enthalpy of mixing. So it will have the same units as the enthalpy, which is nothing but kilojoules per mole. So you can see here, if you keep this as 0 and then make omega s as positive 15, you start developing a eutectic, and we saw yesterday how this eutectic actually develops because of the miscibility gap, and the miscibility gap and the liquidus plunging downwards, and both of them meeting, both the liquidus and solidus and the miscibility gap meeting. Basically what you see down is this is the miscibility gap and this is the liquidus, both of them merge into each other and we will get that. And now if you keep this as constant and let us say make omega L more and more negative, you see that liquid is becoming more and more stable with respect to the solid, and as a result the eutectic temperature starts falling. And you will see the same thing can be also seen if you want to increase the omega s, keeping the omega L the same. For example, if you keep the omega L as 0 and increase the omega S to plus 30, what you see here is that the terminal solubilities on both the sides vanish, and you will also see the liquidus coming down. Like this, we will be able to see how various, and similarly if you keep this as 0 and make it this as plus 30 and make this more and more negative, similar thing happens. So, as the liquid becomes more and more stable, by making the omega L more and more negative, you see that the liquidus line comes down. That means the eutectic becomes more and more deep eutectic. Yesterday I also gave you an idea of how to quantitatively measure how deep the eutectic is with respect to, basically we take the melting points of the two pure metals and then find out what is the melting point of a mixture of the two pure metals at the eutectic composition, and take down what is the eutectic temperature, and the difference between these two will give you a measure of the deeper the eutectic it is, and of course it has to be normalized with respect to the melting point of the mixture, and that is what we have seen in the last class. Now, if you see that if the omega L becomes positive, so far we have seen whether the omega S is positive and the omega L is either 0 or negative, and if you make the omega L start making the omega L positive, then you start seeing the development of the monotectic phase diagram, that you start seeing a miscibility gap inside the liquid. Not only the solid also will have the miscibility gap, but also the liquid also will have the miscibility gap, and you start developing either the monotectic or the syntectic kind of phase diagrams, and that is how you see all the phase diagrams can be. In fact, these though this is schematically shown, in principle one can calculate all these phase diagrams simply by just varying the two parameters, and whole calculation is based on what we have seen, the equilibrium principle, which is nothing but the chemical potential of A in alpha is equal to chemical potential of A in liquid, and if you use this as the starting point for your equilibrium, from that you can find out at each temperature what is the liquidus composition, what is the solidus composition, and from that we can come across all this. And in case there is a third phase to be involved, for example in case of eutectic or in case of a monotectic, you have three phases coming into picture, and you would see how to deal with those three phases by considering a third phase, and that is what we are going to see it today. What happens, how do I consider the third phase? At the moment we have been talking about only two phases, omega S and omega L, and how do I consider a third phase, and that is what we will see today, and that also gives you an idea of how to understand the miscibility gap. Yesterday somebody was asking me, sir, if this is the miscibility gap, how does this get closed? Okay, what is the thermodynamics behind it? We will also see today how, what is the thermodynamics behind this, the miscibility gap getting closed at higher temperature, and why does it get closed. To understand this, what we see is how does the free energy curve look like at that temperature. For example, you take a system which is an isomorphous system and draw a free energy curve at that temperature. How does that free energy curve look like? If I draw it, this is G versus X we are talking, and at this temperature what is stable? Solid alpha is stable, this is liquid plus alpha. So, alpha is more stable, very easy. So, as a result I will see a free energy curve for alpha which looks like this, and of course there will be a free energy curve for the liquid which is something like this. This is liquid, this is alpha. Am I right? And this free energy curve is expressed in terms of the free energy expression that we have given earlier, where G alpha is XA GA plus XB GB plus delta H mixing plus RT XA ln XA plus XB ln XB. So, that expression which we have given can be used to calculate this free energy. This is all fine. The moment you see a miscibility gap here, how does this free energy curve is going to change? The difference between this and this system is that in this system the omega S is positive. am I right. So, there is a positive interaction between the A and B, that means A and B do not attract each other, they repel each other. The moment this is positive, what happens to the delta H mixing? Delta H mixing is positive, because delta H mixing is nothing but omega into XA XB, regular solution model, as long as I assume that regular solution model is valid. So, this is also positive if this is positive. If that is positive, then you would see that if I try to draw, you would see that if I plot the delta H mixing as a function of composition, you would see the delta H mixing curve will be something like this. This is the delta H mixing. Am I right? So, once it is like that and you have the T delta S mixing curve minus T into delta S mixing, which is the second part of the free energy of mixing, will always be negative. The only difference is, depending on the temperature of this value is going to depend. This value, how large absolutely it is or how small absolutely it is, depends on what is the T, because delta S mixing is only a function of composition, it is a symmetric function. We have seen that XA ln XA plus XB ln XB. So, as a result, this is going to be solely dependent on the temperature, and as a result, at room temperature, if I am considering where the temperature is not too high, you would see that possibly this particular value T delta S mixing is lower than the delta H mixing for a certain case. As long as delta H mixing value, the maximum value of delta H mixing is smaller than the minimum value of T delta S mixing, you would see that the delta G mixing, which is nothing but delta H mix minus T into delta S mix, if this is positive, which is what we have seen here, but its absolute value, if it is smaller than this negative value, then the delta G mixing is still negative. If the delta G mixing is still negative, then the free energy curve will be having a curve downwards, as we have drawn here, it will be like that. The moment this value is higher than this, you would see that the free energy curve will look, if I draw now the free energy curve, the free energy curve would look something like this, assuming that the GA and GB are 0. We can always assume that the standard states that free energy of pure A and free energy of pure B is 0. It is an extreme case, of course, it may not be 0. If so, if I assume that GA equal to 0, GB equal to 0, that XA GA plus XB GB term vanishes. Okay, for schematic case, we can just assume it to be 0. So, once that vanishes, then I can write this as G alpha. But at the same time, you may say, sir, why not it goes, the free energy curve go like this? When this is going to be higher than this, why should it have an inflection like that? Why not it goes like this? That is where we have seen in one of the previous classes that the free energy expression, which is here G alpha, even if you assume that the pure metal terms are not there and simply put omega XA plus XA XB plus RT XA ln XA plus XB ln XB and differentiate this and find out the dou G alpha of dou XB and find out what is its value at XA equal to 1 and XB equal to 1, you see that this is minus infinity. I hope all of you have done this assignment and submitted to me. Okay. So, you see that it is minus infinity, and as a result, that means the slope of the free energy curve as a function of composition, irrespective of what is this omega value, however large positive or however large negative, it is, this is bound to be negative and it is minus infinity, and because it is minus infinity on both sides of the free energy diagram in terms of the composition, you see that the free energy has to fall, because the negative the free energy curve should have a slope which is minus infinity towards this end and towards this end. The only difference that you see when you keep on increasing this positive, if this is negative there is no problem at all. If this is negative, what is going to happen? This curve is going to become more and more deeper down. Okay? You will see that this curve will go down more and more if omega is negative. Omega being negative is not a problem at all. The free energy curve is not going to change much, excepting that the shape remains the same, the absolute values are going to change. But if this value is positive, and depending on how large this value is, you would see that this free energy curve could, in an ultimate case, could even be like this, or could even become drops a little and then becomes like this. If the delta omega value is highly positive, then you see it drops by a small extent and then starts rising, and this drop is because of this. So, you would see in all the cases it will never start from 0 and start rising. So, it has to have a drop, and how small it is, how measurable it is, depends on the sensitivity of your measuring instruments, but in principle thermodynamically and in fundamentally it has to come down, and that is what you see here. And the moment you see a curve like this, I can start talking in terms of what is called a common tangent, because this curve is one single curve, but it has an inflection. The slope of it is changing at these points. In fact, we will come to these points later, they are called the spinodal points, and when we talk about spinodal transformation, we will try to understand that in greater detail. But the moment you see a free energy curve like this, then I can start talking about if I start drawing the tangents, you will see at one stage there can be a tangent which is something like this, which is a tangent for both the ends, and this particular tangent where you see the 2 points there, these 2 points are nothing but the equilibrium compositions of the original phase, which is now decomposing into 2 phases because of this limitation of the omega being positive. The A and B are not able to dissolve into each other, so they are forced to segregate. The A dissolves into B to some extent, B dissolves into A to some extent, and they are not able to completely dissolve, and to the extent to which A dissolves into B and B dissolves into A can be obtained from this common tangent. So, that means basically what you see, these 2 points at this temperature are nothing but these 2 points in this free energy curve, and that is why we call this as composition of alpha 1 and composition of alpha 2. Incidentally, you call these as alpha 1 plus alpha 2 and you do not call them as alpha and beta, basically because both are same structures. It is actually one single phase which is decomposing into 2, with the structure remaining the same excepting the composition being different. So, as a result, this whole thing is alpha, and the alpha is splitting into 2 phases, one having a rich composition, another having a B rich composition, and that is how you see that this is happening. We will know more about this as we go to the spinodal and try to understand why spinodal occurs and things like that. Now, if we look at what should happen if this is the free energy curve, if that is the free energy curve which is leading to this situation of alpha 1 having this composition and alpha 2 having this composition at this particular temperature. And mind you, I have to also say that if I am on this side, if I am on this side, what does it mean? You remember that maybe I will draw this in a greater detail for you to understand why this splitting has to occur. For example, imagine a case something like this, and you have a common tangent which is something like this. And mind you, common tangent does not mean it has to be always horizontal. The free energy curves could be like this, it could also be like that, though generally for most of the in the textbooks they show like this. It is not that it has to be a horizontal. So if you take a case of this composition to the left of it and draw a tangent which goes and hits somewhere here, you would see that the whole free energy curve is above this tangent, and in comparison, if I take a composition here and draw a tangent to that, assume that this is tangent, this is the point, you see that if this is the tangent for that particular composition, I am taking a alpha of that particular composition, you see that beyond this particular composition, you see that there are certain compositions which have a lower free energy than that corresponding to this tangent. That means these compositions are stable compositions because their free energy is lower. So, they can in principle come out of this particular composition. So, if I take alpha of this composition, in principle alpha of that composition is not stable. Why? Because in principle I can even show what is the free energy of this free energy of this is this, and if I take a two phase mixture of alpha 1 plus alpha 2 of the same composition, the two phase mixture has a free energy which is given by this, because this is the common tangent. If I draw that line, any two phase mixture, whenever you draw a two phase mixture, the free energy of a mixture can be always found out by the line joining the two free energy curves, free energy points. So, if this is the free energy of the alpha 1 of the equilibrium composition, and if this is the free energy of the alpha 2 of the equilibrium composition, then the line joining these two will give you the free energy. If I have a phase mixture of alpha 1 and alpha 2 with different amounts of alpha 1 and alpha 2, what is the free energy of such a mixture can be always obtained by this line, which is a simple rule of mixtures. And if that is the case, the two phase mixture here has a lower free energy than this, and because two phase mixture has a lower free energy than this, you would see instead of a single phase existing for this particular alloy composition, it would like to exist as a two phase mixture. And that is what you see if you draw a tangent. You see that the phase here, which is a B rich phase, having compositions, all these compositions, any one of those compositions can in principle nucleate from this particular alloy, because this alloy has a higher free energy than the two phase mixture. Which one will actually nucleate, we will see when we talk about what is called the spinodal. We will know more details about it, which phase should actually form, and in principle usually the one that forms is the one which has the highest driving force, and the highest driving force can be obtained by the difference between this and this. This will give you the highest driving force. So, as a result, that is the composition which would try to nucleate. We will know more about it when we go to spinodal, but at the moment you can understand that if I take this particular alloy composition, a composition of this, you see that none of these particular compositions have a free energy lower than this line. As a result, none of them can nucleate from an alpha of this composition. That means what? The alpha of a single phase alpha is stable at this particular composition. But if I take this particular composition, single phase alpha is not stable, it wants to split into 2, which is alpha 1 plus alpha 2, and alpha 2 will nucleate out of that alpha, and whatever alpha is left out is what we start calling it as alpha 1. because the moment you see that alpha 2 of this particular composition nucleates, then immediately there has to be an equilibrium between that alpha 2 and the alpha. For example, if you have an alpha from which alpha 2 has nucleated, this alpha 2 has to be in equilibrium with alpha. What particular composition of alpha that can be in equilibrium with this alpha 2? If you try to look at, if this is alpha 2, the composition of alpha that can be in equilibrium with alpha 2 is only this composition, because the one that can come as a common tangent. When you draw the common tangent, you would see there where this common tangent touches the alpha, that is this composition, that alone can be in equilibrium with this alpha 2. You cannot have this particular composition in equilibrium with this alpha 2, because I cannot have a common tangent between that and this. It is not possible to have a common tangent. That means what? The moment alpha 2 comes out of alpha, the composition of alpha surrounding this particular alpha 2 changes, and actually it becomes poorer in B and richer in A. Why does it become poorer in B? Because it is alpha 2 which is rich in B is coming out of alpha. As a result, the alpha which is surrounding that will lose the B atoms, because all the B atoms are coming together and forming an alpha 2 phase, and because the alpha 2 phase is coming out, the alpha which is around that will lower its B atoms, and as a result the composition of alpha shifts towards pure A side, such that that particular alpha becomes in equilibrium with the alpha 2. So, that alpha which you see it around this alpha 2, we will start calling it as alpha 1. So, now that alpha which is so far away from this alpha 1 and alpha 2, you may still have the alpha having this particular composition until the whole reaction is complete. At the beginning of the reaction, you will see the alpha 2 will come out, and around this alpha 2 always you will have alpha having a composition which is decided by this common tangent, and that is what we will call it as alpha 1, and this is what we call it as alpha 2. Alpha 2 is B rich and alpha 1 is A rich, and this is how you see this happening. And similarly, if I choose a composition here for the alpha, again you will see that if I draw a tangent there, you will see all these free energy points. That means free energy of any of these compositions is higher than this tangent. So, as a result nothing can come out of that particular alpha. So, single phase alpha is stable. At that, everything we are talking at a particular temperature T, because free energy composition diagram is always drawn at a fixed temperature. We are talking at that temperature, let us say the temperature is this temperature. So, at this temperature, to the left of this point single phase alpha is stable, to the right of this point again single phase alpha is stable. That is what this free energy curves tell me, and between these 2 points single phase alpha is not stable, and that is why whether I choose this composition or choose this composition, if I draw a tangent here, you will see all the compositions to the left of this can precipitate out of this. So, that means from alpha 1 will precipitate, and everything will be inverse of what we have talked so far. Once alpha 1 comes out, alpha 1 is A rich phase. As a result, the A atoms from alpha have to come together and form the A rich alpha 1 phase. As a result, the A atoms in the alpha surrounding the alpha 1 will deplete in the A atoms, and that becomes the alpha 2. So, you will have alpha 1 surrounded by alpha 2. In the previous case, it is alpha 2 surrounded by alpha 1. So, depending on whether you are taking a A rich composition or a B rich composition, this is what would happen. This keeps on happening until you will reach the whole composition of alpha 1 and alpha 2 reach these 2 compositions, which is what the free energy concept tells you at that temperature, that these are the only 2 compositions which can be in equilibrium. No other compositions can be in equilibrium. So, slowly you see that the alpha composition changes and the alpha 2 composition remains what it is according to the phase diagram, according to the free energy composition diagram, and the remaining whole alpha vanishes, and you will have alpha 2 growing at the expense of alpha. and you would have alpha plus alpha 2 and alpha 1 at the end of this. We will know more about it when we go to the spinodal, but at the moment what you need to understand is that this is how we will know that these any composition that I choose here, here, you will see all these compositions have a higher free energy than a two phase mixture. The two phase mixture composition is this given by this, and as a result a two phase mixture is more stable in this between these 2 points, and these 2 points are called binodal points. We will talk about this again when we come to spinodal decomposition. So, what you see is that you will see between these two there is a alpha 1 plus alpha 2, and we call it as alpha 1 and alpha 2 because both of them have the same structure. We do not call them as alpha and beta. The moment you bring in a beta, that means you are talking of a different structure. So, this is how you see this happening. Now, what should happen if I increase the temperature? What should happen if I increase the temperature? This delta H mixing, is it a function of temperature? Actually yes and no. Okay. According to this it is actually no, but if you carefully look at this omega, omega is what? Interaction parameter. It tells you actually about how strong is the AB bond, whether A and B attract each other or repel each other, and these bond energies are in principle function of temperature. So, in principle there are models that are available where omega is considered as a temperature function, and if you go to CalFAD journals and CalFAD, the book that I have told you, Kaufman and Bernstein book, you will see where omega is also taken as a function of temperature, but for most of the basic thermodynamic understanding, people consider this to be constant. If this is constant, the only temperature function is this, and this being the whole thing being negative, because this whole thing is minus T delta is mixing. So, this whole thing being negative, so you would see that this keeps on going more and more negative as I increase the temperature. As it becomes more and more negative, what you will see, because this is fixed, delta H mixing is fixed, and this is becoming more and more negative, you see you will reach a stage where this free energy curve changes from this shape to this shape. You would actually see that this free energy curve slowly starts becoming like this, and then it further becomes like this, because this hump starts decreasing, because the negative value of the entropy of mixing is becoming more and more, and you would see at some stage the free energy curve becomes like this, and beyond that temperature the free energy curve becomes more and more negative again, because this is much more negative. You can see that just looking at the T delta S mixing term, we can understand how this free energy curve, which has a concave and convex mixed, is getting converted to one single type of free energy, which indicates stability. We will also talk about how stability is related to this when we come to the point of spinodal. So, this is an indication of stability, and this is an indication of instability for free energy. We will see why it is so when we come to spinodal decomposition. At the moment you just leave it. So, the moment you see that this free energy curve, that means there is the any, for example, if you take any point here, a composition here or here or here or here, if I draw a tangent, what does that tell me? That all points, free energy points, that means at any given composition free energy of all these compositions is above that of tangent. So, there is no chance for any other composition to precipitate out of alpha of this composition. I can see that from all the compositions. Anywhere I choose a composition and draw a tangent, you would see all the whole free energy curve is above that of the tangent, and because it is above that of the tangent, there is no chance for this. That is why this free energy curve indicates its the single phase is stable, and that is the reason why above this particular temperature, if you come to this temperature, you will see the free energy curve becoming like this. and that basically means that this has to merge. And you will also see as you go to higher and higher temperature, these compositions start coming closer, and that is what you see here also. As you go from this to anything like this, for example, if you see there are too many curves here, that may confuse you. For example, if I take this free energy curve, draw a common tangent, you would see, maybe I will show you here. If you see this is this decreasing like this, and draw again a common tangent, you would see these points would be inside these 2 points. That means the equilibrium compositions, the binodal points, are shifting towards each other as the temperature increases, and to an extent that you would see that slowly they start coming closer and closer, to an extent that at some stage they both become merge into each other and become one point, and that is this point that you see here. And that temperature, in principle, how do I calculate that temperature? Can you tell me? Can I calculate that temperature? Should be very easy. What is that temperature? Where this should happen? You simply equate this with this. Simply equate this with this. You can find out what is that T. And again, that is not sufficient, something else you have to do. Equate it and put one boundary condition, xa equal to xb, because both these functions being symmetric, this actually happens at 50-50. So equate this to this and then take xa equal to 0.5 and xb equal to 0.5, and once you take that, you would be able to find out this T, which is this. In fact, you would see when you calculate this later, you would see this will become equivalent to that, we call it as T star, and the T star is omega by 2r. One can do this calculation. And so the higher the omega value is, the higher the omega value is, the higher will be this T star. That is what yesterday when we are talking about, as I increase the omega more and more, or in other words, as I increase the size factor more and more, you would see that this temperature increases. Initially it was, the miscibility gap was like this, then the miscibility gap has become like this. So this temperature has gone up. When I increase the omega, this temperature goes up, and that is what you see this happening. So like this, we can in principle find out how this miscibility gap closes. The temperature at which the miscibility gap closes can be easily found out by equating this with this and then finding it out. In fact, it is not so simple also. We will see as we go along, when we go to spinodal, there is also another way to find out by taking the second differential of the free energy. How to do that we will see when we go to the spinodal. At the moment you take it this way. Is this clear now? So let us now look at, yes. So like according to the principles of diffusion, we should have a tendency to diffuse into alpha 1, right, so that the concentration of P is equal. Okay, let us see. This is all alpha, starting with alpha. We are talking of a situation where a free energy curve is like this. We are talking of a composition like this. This is the starting composition. Let it be 20% or 30% B. That is alpha, and in this alpha, now alpha 2 having this particular composition has nucleated. This is alpha 2 which is nucleated, and that has how much? This has much more B content, isn't it? And how does this nucleation occur? That is where another question is. You say, sir, alpha is containing only 30% B. and if it is 30% B, then how can in a 30% B which is uniformly 30% B, suddenly you will have a nucleus of the alpha 2 which has a 70% B coming out. This is where you need to understand that every liquid or solid, you at any given temperature there is always vibrations, there is always atoms moving, and there are always clusters of varying compositions. Though overall the composition is 30%, you can have a small region which is a few nanometer region or even a less than a nanometer region, where the atoms are more concentrated in terms of either A or B. But the question is, according to thermodynamics, at a given temperature, if this alpha is not stable, then those clusters which have a B content of this would get stabilized suddenly, and that particular clusters will start growing. That is what we call it as R star. This is how even liquid to solid transformation. You may say, sir, liquid is completely random, how does suddenly solid nucleate? Because there is a short range order inside the liquid, and inside the short range order you see some clusters having a particular crystal structure. They may be 100 atom clusters, 10 atom clusters, 1000 atom clusters, different sizes do exist, and once a particular size of the cluster has the value of R star for that particular temperature, that particular cluster starts growing. So let us assume that there are clusters. So that B has nucleated. How it has nucleated, let us not bother about it. Now once it is nucleated, this is alpha 2. Now this particular alpha 2, can it be in equilibrium with this alpha? It is not possible, because I cannot draw a common tangent between these two, impossible.
So that free energy is responsible for keeping B inside alpha 2.
Yes. So this inside alpha 2 is because this alpha 2 is stable, it has a low free energy with respect to that alpha. With respect to that alpha, because it has a low free energy, so it tries to come out. But once it comes out, because this cannot be, the only way this alpha 2 can be stable is either to dissolve back into the matrix or change the alpha around it, its composition, such that it can exist with that. It is like, if you want to be friendly with somebody, you change your attitudes or change your friend, so that you are in kind of harmony with the other friend. Exactly the same way here. So if you want alpha to be alive, it can be alive only if alpha around it changes its composition, such that you can have a common tangent between those two. That alpha alone can be in equilibrium with alpha 2. So as a result, because already from the alpha B atoms have come together to form alpha 2, then obviously this alpha has given out some B atoms. Because it has given out some B atoms, its B atoms will decrease. So in a small domain, like this, the B atoms have decreased, and when they have decreased, that means the composition of alpha has actually started moving in this direction. Only at least a small region, it might not have happened in the whole alpha, but at least just around alpha 2 it would happen, and that particular small region around this, I will call it as alpha 1, and that composition will reach this particular composition, so that this alpha 2 can be alive. Otherwise alpha 2 cannot be alive, it has to dissolve back. This is a major problem. That is why we will see alpha 1. And now what should happen in future? This alpha 1, alpha 2 is there, then alpha is also there. So finally at this temperature, in principle what is stable is only alpha and plus alpha 1 plus alpha 2. And what is the driving force for that? The driving force is this minus this is the delta G. That is the delta G for the alpha to give you alpha 1 plus alpha 2. That is the driving force. So driving force is available, the only thing that you need is diffusion. So if the diffusion takes place, then what you will see is this alpha slowly vanishes, the alpha having this composition, because it is not stable, it slowly starts giving out the B atoms more and more, so that the alpha 2 starts growing, and as alpha gives out more and more B atoms, what happens, the alpha becomes poorer in B, and so that the whole of alpha. So, after some time you would see a situation like this, that the alpha 2s have grown, these are all alpha 2s, because the B atoms are coming continuously and flowing into the alpha 2 from the alpha, and as they flow into this, you would see alpha 2 increases, and the remaining alpha completely becomes alpha 1. So, you will have a alpha 1 matrix and alpha 2 precipitates inside, and this can be seen very easily if you look at there is a gradient between this and this. Why does there is a gradient come? For example, you can see the moment you see a situation, I see a case where everything is alpha with a certain composition initially. Suddenly you see a beta, alpha 2 comes out. If the alpha 2 comes out, alpha 2 has a much higher composition than the alpha, isn't it? So, as a result, this is, if I call this as alpha 2, which is coming out, the remaining is alpha, but this alpha 2 cannot be in equilibrium with this alpha. So, what is that it can be in equilibrium with? So, it is this value. So, you will see that alpha 2 will be in equilibrium with alpha having a composition which is much lower than this alpha. So, you will see that this will be actually, if I draw the concentration profile, it looks like this. This is the alpha, this is the alpha 1, this is the alpha 2. So, you would see a concentration profile something like this. Just adjacent to alpha 2, alpha will have a lower composition, but away from the alpha 2, alpha will have the same composition with which you have started. Now, what happens is, if you see, there is a gradient here. B atoms are more in this, everything I am talking in terms of percentage B as a function of distance. So, initially everything is alpha, and inside that alpha 2 has come out, and alpha 2 has a higher B content, and because this alpha 2 has to be alive, it can be in equilibrium with alpha having a lower B content than what it is. That is what you see, this is the starting alpha, this is the alpha composition which is lower than the thing. So, now you see there is a gradient. Because there is a gradient, you would start seeing that B atoms are flowing from this alpha towards this. Then what should happen? Slowly this will grow. This will start growing more and more. But will this change? Will this composition change? This composition is an equilibrium composition of alpha 1 in equilibrium with the alpha 2. So, that cannot change. Then as this grows, something else should happen. What should happen? Amount of alpha, we are not talking of amount now, we are talking about in terms of concentration, anything should happen. Of course, amount of alpha will decrease because alpha 2 is increasing, alpha will decrease. Anything else should happen to the composition of alpha? Will go down. So, as a result, you see that this curves, as this grows, you would see a situation when it becomes this. This B content in the alpha has to come down because it is giving away, it is like a reservoir giving the B atoms to the alpha 2. As it keeps on giving more and more atoms to alpha 2, the amount of B atoms in the alpha should come down. So, this particular value comes down, and as this comes down, you will see a situation where finally the whole alpha around this alpha 2 will have the alpha 1 composition. Then we will call this whole thing as alpha 2, alpha 1, this as alpha 2. So, now it is alpha 2 and alpha 1. Of course, kinetically if I look at it, because if this is happening as the alpha composition is decreasing, the gradient is coming down. That means dC by dx is coming down. You know that J is minus d into dC by dx. If the dC by dx is coming down, then what should happen? The flux should, so the reaction will slow down. So, the growth of alpha 2 will slow down with the time, that is fine, but thermodynamically finally it should come to this, and that is how you see that remaining alpha will be called now not as alpha, it will be called as alpha 1. So, that is how you see one single alpha has become alpha 1 plus alpha 2, and the same thing can happen in a different fashion in a spinodal. We will know how it happens when we come to spinodal. Okay. So, you can see that this is how splitting takes place, and as you increase the temperature, this is how you see this gets closed up. Okay. I think with this we will close for today, because I wanted to start another concept which we will start in the next class.
Sir, will it eventually, when the transformation is complete, alpha changes to alpha 1 plus alpha 2, the overall composition of D, will it still be 30%?
Obviously, that is, mass balance has to be maintained. So, because the mass balance has to be maintained, the only thing is we can write an expression. Now, the fraction of alpha 1 into the composition of alpha 1 plus the fraction of alpha 2 into the composition of alpha 2 should be equivalent to my C naught with which I have started. So, the amounts of alpha 1 and alpha 2 will be adjusted in such a way that these compositions will give you a particular amounts. So, we can, this is how actually our lever rule comes. How do you get a lever rule? It is only this. Okay. We will stop.